Having taken a look at count vectorization and in-rem vectorization, in this chapter we take a look at term frequency, inverse document frequency, or popularly known as tf-idf way of vectorization. Hi, this is Shanko and welcome back to NLP with Python. So let's first take a look at the formal definition for tf-idf. The formal definition goes as in information retrieval, tf-idf or tfidf, short for term frequency inverse document frequency, is a numerical statistic that is intended to reflect how important a word is to a document in a collection or corpus. It is often used as a weighting factor in searches of information retrieval, text mining, and user modeling. The tf-idf value increases proportionally to the number of times a word appears in the document and is offset by the number of documents in that corpus. In the corpus that contain the word, which helps to adjust for the fact that some words appear more frequently in general. tf-idf is one of the most popular term weighting schemes today. So basically tf-idf tries to find out how important a word is in a corpus of documents or in a corpus of words, and the term or the word should not be appearing a lot of times in the document. So tf-idf is represented by this formula, and this might look intimidating right off the bat, but it's quite simple to understand. So let's try to understand this part first. tf-ij, so this stands for the number of times a particular term appears in a document divided by the total number of words inside the document. So if you're dealing with this sentence, I love NLP, and we are trying to find out the wij for this word NLP. So NLP occurs once inside this document. So there are 3 words inside this document, and NLP occurs once, so that would be 1 by 3. So tf, so let's write this down, tf for NLP, and let's call this the first document. So tf of NLP and 1 would be 1 by 3, 1 divided by 3, so that is equals to 0.33, right? Yep, 0.33. And now let's try to understand this part, the log part. So this n stands for the total number of documents inside the file. So let's suppose we have 20 documents inside the file, so n would be equals to 20. So n equals to 20, and let's try to understand this tf. So this tfi stands for the number of documents which contain this word, right? So let's suppose this is contained by just one word, so again that would be tf of I would be 1, right? So the tf-idf for the w for this word NLP inside this document or inside this file would be 0.33 into log of 20 by 1, right? So that's how we define the wij for NLP inside a file which contains 20 documents, and this term NLP appears in just one document inside the file. So that is how we would describe, or that is how we would find out the value of wij, right? Now enough of theory, and let's try to understand how to implement using code. So we'll be using the same techniques or same steps that we have been doing in our previous two chapters. We'll be reading in the text file, or we'll be reading in the file called SMS spam collection. And just for a reminder, we are working with this file here, which contains a list of messages which are classified as ham or spam, and we are trying to create machine learning classifier or a machine learning model using this file that we have, right? And so instead of using count vectorizer, I'd be saying tf vectorizer. So it belongs to the same library sklearn feature extraction text, and then we'd be reading in the data, and we'd be setting the columns for our data set. So one would be label that would be either spam or ham, and the text would be the actual text message, right? So in a previous chapter, and we'd be using the Porter stemmer for stemming our words down to the root words, right? So in a previous chapter, when we had used when we were using n-gram, instead of returning the tokenized list of words, we were actually returning a sentence, a complete sentence. But now again, we would be returning the tokenized list of words, right? So let's try to run this. All right, so we won't be needing this, and let's just try to run this first and see everything is working. So everything seems to be working. Now let's try to use the tf-idf. So I would say tf-idf underscore vect equals, so first we'll be creating the vectorizer. So I'd say tf-idf vectorizer, and we'll be passing in the analyzer, and we need to write the name of the method that cleans up the data. So we'll be cleaning using the clean text method. And let's call this tf-idf underscore counts equals tf-idf dot fit transform, underscore vect dot fit transform, and we'd be using the data set, and we'd be using the text column for the data set. So I would say text inside this, and then let's try to print the shape of tf-idf underscore counts dot shape. Let's try to print this. Alright, so we have 5572 number of rows inside our document or matrix, and we have 8192 columns inside our document or matrix. So the document or matrix still contains single words as a column, single individual words, individual and unique words as the columns, and the number of rows also represent the number of documents inside our file. And let's try to convert this to a data frame. So I will remove this that we did in our previous lesson, and I would say I would call this tf-idf underscore df, so that's data frame, equals pd, so that's for pandas library that we have imported here as pd. So pd dot data frame, and I would pass in this tf-idf counts, and this again is stored as a sparse matrix in Python, and we have already talked about what sparse matrix is in our previous chapter, and how Python stores the sparse matrix in the memory. So we need to expand the sparse matrix. So I would say to array, and let's try to assign names to the columns inside our data frame. So I'd say tf-idf underscore df dot columns equals, so I would grab this tf-idf underscore vect dot get feature names, right? So those would be our columns inside our data frame, and let's try to print our data frame. So let's say tf-idf underscore tf dot head. So that would print the first 5 rows inside our data frame, right? So let's try to run this. So we can see we have this kind of a matrix as our data set or as our data frame. Let's try to print the first 10 records or the first 10 rows inside our data frame. All right, and let's try to take a look at the last 10 records inside our data frame. So I'd say -10, and I would not say anything for the other thing for the range. So we can see instead of having instead of integer values, we have some decimal values, and this actually signifies how important this term is or how important this word is. And let's try to take a look at the last 20 rows inside a column, inside a data frame, and most of these are 0, so that is why this is called a sparse matrix. Or let's try to take a look at the first 20 rows inside a data frame. So again, we have all zeros, almost everything is 0 inside this. And let's try to take a look at the 20th to 40th. And 100 to 120. So almost everything is 0, and that is the reason this is called a sparse matrix. And basically tf-idf tries to find out how important a word is when in a document or in a collection of documents in a file, and the word should not be appearing very frequently. So if a word is appearing frequently in general, that is not considered as important for creating a feature or while making a prediction. So we try to understand how important a word is in terms of how frequently it occurs inside our file, and that is how we can vectorize using tf-idf or term document or term frequency inverse document frequency. So that is all for this chapter, and in the next chapter we're going to talk about feature engineering. So stay tuned for the next one. Bye.